Hello everyone, welcome to the next lecture of our Blockchains Architecture Design and Use Cases course. So in this lecture, we're going to look at a very important aspect of blockchains, and it's also an aspect that has been seeing a lot of research activity, a lot of innovation, which is really privacy. If you look at blockchains as such, right, it's about decentralization, having multiple peers holding a replica of your data. The smart contracts are also replicated and decentralized. So the notion of privacy is really at odds of this notion of replication and decentralization. So how do you ensure that your transactions are seen only by a certain set of people? How do you ensure your data remains private and confidential? So the notion of privacy and the notion of replication and decentralization are really at odds, and there are very interesting innovations that are coming up that allow you to achieve both notions, right? Both privacy as well as decentralization and replication across multiple nodes in the network. So in this lecture, we'll look at what are some of those innovations that are, all of these are very new concepts, right, within the last 5 years, I would say. So when we look at what we are storing on blockchain, so there's really multiple things we are storing, and the notions of privacy are also, for that reason, there are many notions of privacy. So what do we really mean by privacy? So first of all, blockchain is going to store a set of transactions. So there is transaction privacy. There is transaction privacy, which means that I want to keep the inputs of a transaction, basically what smart contracts I'm executing, what are the input parameters. I want those to be kept private. So that's the transaction data privacy. There's also the state data privacy. So this is the internal state that is maintained by the smart contract and is recorded onto the ledger. So we want that data to also be private. And note that the transaction data is just the inputs to the function, right? The state data is really what the function is actually computing, and it could be more than just the input parameters that are sent in. The third thing is the contract privacy itself, which is the logic of the chain code, which is really the code, which is also going to be residing on the blockchain. We want to keep that private, right? We want to only expose that code to a certain set of authorized entities. And the final notion is of that of user privacy, which is the fact that who is performing this transaction, who is endorsing a transaction, the user level credential details we want to keep anonymous. And the other notion along with anonymity is that we also want unlinkability, which means that when one user performs, let's say, 100 transactions, no one should be able to say that these 100 transactions were really performed by one user, right? Those 100 should appear as though they are really coming from independent entities. So that's the notion of unlinkability. So we want privacy at the level of transaction details in terms of state data, in terms of the logic of the chain code, which is the smart contract privacy, and also user privacy. And none of these aspects of privacy are supported by the many permissionless blockchain platforms we have, like including Bitcoin and Ethereum. They only provide a notion of pseudo-anonymity, which is to say that I as a user, I can assume a pseudonym. People will know that that pseudonym is performing transactions, but they can't link the pseudonym with the original user. But apart from that, it doesn't provide any notion of transaction data or state data privacy at all, right? And it's left to the applications to explicitly handle these notions of privacy. And these notions of privacy are actually very important for many of the enterprise use cases. For instance, if I'm storing healthcare records on blockchain, the healthcare records are sensitive information. So I want to make sure that the data that I'm storing is actually private. It doesn't matter whether I'm storing it on blockchain or otherwise. The intent from the use case or the industry is that that data has to remain private, and it can only be authorized for certain users on a need-to-know basis. Right? Let's say the other example is when a bank or banks are transacting or enterprises are exchanging money or assets between each other, they want to ensure that their user information is private. They don't want to know how much money is getting transferred between enterprises. So we want that notion of privacy and only authorized entities should be able to see critical information. So now in this lecture, we'll look at various ways in which some of these notions of privacy can be achieved in a blockchain platform. Hyperledger Fabric, as a permissioned blockchain platform specifically targeting enterprise use cases, has several constructs that all help provide different notions of privacy. So it's then up to the application designer or the user to leverage the privacy in the right way. Right? So we'll look at some of those constructs, and we'll look at also some constructs that from other platforms along the way. Right? So the first notion that Hyperledger Fabric provides is the notion of channels. Right? So channels are really a partitioning mechanism whereby different subsets of entities in the network can all come together to form one channel, and all data within that channel are only available to the participants of that channel. So participants who are not part of the channel will not be able to see anything about the channel. They won't even know the existence of that channel. Right? So it's really a partitioning mechanism, and in some sense each channel maintains its own chain of blocks. So the ordering itself is independent across channels. So you could have different ordering services for each channel. So each channel can have its own ordering service. And those transactions are treated separate. So one of the things you cannot get is, for instance, you can't have a transaction that really spans across channels. So each transaction is restricted to a particular channel. And that also means that if you want to do something atomic, which means that I want two transactions to happen on two channels, I can't make that happen atomically using the platform itself. So the application will have to take care of that atomicity. Then coming to channel creation, who can create channels? Only authenticated and authorized users will be able to create a channel. Specifically, the channel creator, whoever is creating the channel, has to be a network administrator. The channel creation request is submitted and is evaluated by the ordering service. The ordering service will check whether an authorized participant is trying to create the channel, and along with that request to create a channel, you also specify who the participants are going to be, right? So it is going to be restricted to a subset of the organization's participants, and the participation is defined by three policies. One is who are going to be the readers. So the readers, in some sense, you can think of it as the ones who are just going to be committing data, right? They'll be able to read data. All they're doing is committing transactions. They're not doing anything else. The writer policies is who can write data into this channel, right? So they'll be the writers, and the admin policies are the ones who are able to perform administrative functions. For instance, only an admin will be able to install a chaincode, instantiate a chaincode on a particular channel, right? Likewise, only an administrator will be able to change the channel configuration parameters. So all those are administrative functions. There are, of course, readers and writers onto that channel. And you can specify in a granular manner who can read, who can write, who has administrative privileges, right? And so this whole notion of channel, in some sense, provides both transaction and data privacy to a subset of the members of the channel. So all the members of the channel will have rights to see what transactions are there, what data is being stored in the smart contracts. But within a channel, we don't have privacy with this construct, right? It just allows you to partition transactions and data in the network. And all members of a channel will see all the data within it. Note that the data privacy is not offered with respect to the ordering service. So the ordering service for a particular channel will see the data within the channel. And with just using channels, you can't get data privacy with respect to orderers. So orderers will see the data. And there are other constructs that will help you even obfuscate that from the orderers. So the second construct is, of course, you can use encryption, right? So this is a well-known technique for decades, using encryption for ensuring privacy. So you can encrypt the data and share the key only with authorized entities. And that way, only the authorized entities will be able to decrypt the data and see the original content. Everyone else will see just the encrypted data, and with that, they can't figure out what the original text is. So this is a well-known security primitive, just using encryption. But then the application will have to do this encryption, at least in most of the blockchain use cases. Otherwise, you don't want to share the key on the blockchain. That way, then everyone will get the key, right? So then you're losing your privacy, right? So once you encrypt the data at the application layer, the application now has to maintain these keys. Now even the peer will not see the unencrypted data, right? But then if the chain code is also only going to get the encrypted data, and all it will do is just store that data, and it'll be able to retrieve that encrypted data. Now the disadvantage is that it's going to be very hard to manipulate or validate what that data is. For instance, I can't do arithmetic operations, I can't do conditional operations. Yes, there are constructs like homomorphic encryption that do allow you to perform certain certain functions on that encrypted data itself, but it's not. It comes at a performance penalty, and there are certain disadvantages to doing that, right? Alternatively, you could store private data off-chain, right? You can store it in an external data store, ensure that the right parties have availability of the data, and just have the hash and metadata information stored on the blockchain. So that will give you the immutability. So if someone goes and changes the external data store, the data in the external data store, anyone can actually check the hash on the blockchain and determine that something is wrong, right? The hash doesn't match anymore. So you know that at least you can detect that someone has changed the data or tampered with the data. So this gives you immutability, but doesn't give you all the other advantages of smart contracts of being able to modify the data in a decentralized fashion on a blockchain network. Right? So that's about application layer encryption. Right? The other thing you can do is with Fabric, you can actually send the encryption key to the chain code. So now you're going to let the chain code also see the decrypted content. So how does this work? Right? So chain codes have this field called transient data. Right? So this is a data field in your chain code parameters. So when you're invoking a chain code, you can also add a transient field and send some secret information in the transient field. Right? So when you send that information, the chain code will be able to retrieve this transient field information, but that information is not included in the transaction. So if you see the transaction, it will have the chain code that's invoked, it will have all the parameters, but the transaction itself will not have the transient field. That's why it's called transient. Right? Now what the chain code can do is it can use that transient key and store data encrypted on the peer. So that way the peer will not really have the decrypted content, but the chain code itself can work with the decrypted content, can encrypt and decrypt using that key. Right? Now this, along with leveraging, let's say, a trusted execution platform such as Intel SGX or IBM Z Secure containers, it's possible to isolate the chain code container from the peer. So that way the chain code will execute in a trusted environment, and even if the chain code is handling the encrypted key and is decrypting the content, the peer will not get to see that content at all. Right? The data, when it gets to the peer, will be in encrypted form and will be stored in encrypted form. Right? So it's possible to do that. So this picture just gives you the flow of how that works. Right? A blockchain user is going to use a client application to invoke a transaction on a particular chain code. So what they will do is they're going to encrypt the transaction input parameters. So all the input parameters that's going to go into the chain code, they're going to encrypt it. And of course, the transaction is going to be signed with the enrollment certificate. So this enrollment, the key there is different from the encryption key. So the key you use for signing is not the same as the key you use for encryption. And for different data parameters, you can actually use different keys. And what you're going to do is send the keys to the chain code through the transient field. Now the chain code can actually decrypt the transaction input. It can perform certain whatever functions it needs to perform. It will then encrypt the state data and then store it onto the blockchain. So when it gets to the peer, and what you will see on the block itself, on the blockchain, will only be encrypted data. So overall, this whole notion can be used to encrypt the transaction parameters. It can be used to encrypt the chain code logic itself. Just the code itself is going to be part of a deploy transaction, right? So that can also be encrypted, and the chain code state can also be encrypted, what you're storing on the blockchain, right? So all of these are now possible with Hyperledger Fabric. So the transient data itself it's not included in the endorsement method, it's not included in the transaction, and it's provided to the chain code upon request, right? And how do you leverage it? It can be used for sharing confidential data like key material. It can also be used as a source of randomness, right? So typically chain codes, you do want it to execute in a deterministic fashion. How many ever peers execute it, right? So even if multiple peers are executing the same chain code, you want that to be, the execution to be deterministic. So you don't want any kind of randomness to come in. But what you can do is you can send in a seed, right? So that all of these peers will generate the same random number, but it will be random for each transaction, right? So that source of randomness can also be sent to the chain code using this transient field. Okay. So the next notion, so we looked at how channels can help transaction data and transaction and data privacy. We looked at encryption and how the transient field notion in chain codes can actually give you different notions of encryption and privacy. The third thing is, how do you ensure that the code itself is going to remain confidential, right? So now there are two parts to this. The first is it's important to understand the deployment process in Fabric. So how do you deploy a chain code? There are two steps to it. One is the installation step, and the second is the instantiation. So the installation is really about being able to have the logic in a particular peer. So this is independent of channels. On the peers where the chain code is installed, the peer will have that logic of the chain code, right? So this is just based on the peers. So which peers have to run this code, they will have the chain code. So that's the installation, right? So the next part is a channel specific instantiation. So based on, for each channel on which you want to instantiate a chain code, you will call an instantiation transaction. And at that point, you will say who are the authorized peers who need to execute this transaction and may act as endorsers for this transaction. So that is the second notion. So the fact that endorsers can be a subset of all the entities in the channel means that the logic only needs to reside with the endorsers. So let's say my channel has 10 participants. I can say only 5 of these 10 participants, a specific set of 5 participants, are going to be endorsers, right? So only those 5 will then have the chain code logic. The remaining 5 will not have the chain code logic at all, but will see the transaction data, will see the chain code's data, but they will not see the logic or the code of the chain code itself. So only endorsers will have the code. And within those endorsers, of course, you can have the endorsement policy. So you can say for a particular transaction, 3 out of 5 endorsers have to sign, right? But only the 5 people will have the code itself. Right, so this ensures smart contract confidentiality. So only the peers for a particular channel that need to execute the transaction, who are going to act as endorsers, will or can hold the smart contract code, right? And the endorsement model provides the resiliency to non-deterministic chain code. So given that multiple endorsers will endorse a particular chain code, you can ensure that that code is deterministic, right? Okay, now coming to the next notion, right? So we are coming to the notion of user privacy now, right? So right now there is there's Identity Mixer, which is really an open source project from IBM. It came from the crypto world, but it's now being adopted by Hyperledger Fabric itself. It's going to come in the next release, version 1.2 of Fabric. The development is already underway. I think we briefly talked about this in an earlier lecture. But Identity Mixer gives you very strong guarantees on anonymity and unlinkability. So let's look at how, at least at a high level, how this works, right? So there is a blockchain user. So as before, they have to obtain a certificate from a certificate authority. So there is a membership service provider that interacts with the certificate authority to issue certificates. And there is a enrollment certificate as before, right? But now the user is going to, when they invoke smart contract transactions, so when they invoke transactions, previously we had mentioned that the transaction is going to be signed by the enrollment certificate. Instead, what is possible with Identity Mixer is that the user can generate per transaction certificates. So these are specific one-time use certificates that the user can use for each transaction. And they can also have other one-time use keys that are generated just for encrypting data, like I talked about before, right? So you can generate keys for signing, you can generate keys for encryption, and all of these, it's possible that the user can actually prove that they were all these keys were derived from their enrollment certificate, right? So that is really a unique ability where the user can generate multiple keys from an original eCert, but they can also prove to an auditor that these were all generated by that eCert. So the auditor can come in and see that these transactions were all performed by the same user, but no one else in the system will know that they were performed by one user, right? So that's the difference with the eCerts and the tCerts. The transaction certificates will be one-time certificates that the user can generate to perform transactions on blockchain. So now, because all of these tCerts look different, right? If the user is performing 10 transactions, they can all have 10 different keys. So it will appear as though these were performed by 10 different users. So that way you achieve unlinkability, right? So let's just compare the previous X509 certificates that I talked about with Identity Mixer. So think of Identity Mixer. Identity Mixer is really another Fabric CA and a Fabric or a membership service provider implementation, which is distinct from the Fabric CA that we talked about earlier. The previous Fabric CA was based on X509 certificates, and we'll see how they are different, right? So on the left is how X509 roughly works, right? So there is a certificate authority that is going to issue a certificate to a user, and this certificate can have multiple attributes. So we've called out attribute 1 and attribute 2. So now the user has one certificate with two attributes. So they have these two, attribute 1 and attribute 2. And whenever they perform a transaction, they're going to sign with that certificate. So anyone else who is seeing this transaction will see both their attributes. So that way they'll know that this was performed by this user, so there's no anonymity there. And there's also no unlinkability. So between these two transactions, I know that these were both performed by the same user. So in this model, in the previous Fabric CA, there was no anonymity or unlinkability. So let's look at Identity Mixer and what it does, right? So the Identity Mixer, the CA for Identity Mixer, issues like before an enrollment certificate. It has, like before, two attributes, attribute 1 and attribute 2. Now what the user can do, independent of having to talk to the certificate authority, they can have a presentation policy. So there can be two policies. Based on policy 1, it can choose to just disclose attribute 1. So it generates a transaction certificate that has just attribute 1. And policy 2, based on policy 2, maybe this can be even a different channel altogether where the user is performing transactions. It can be maybe a different chain code, or just simply a different transaction within the same chain code. For transaction A, I want to disclose attribute 1. For transaction B, I want to disclose attribute 2. So if you look at this, attribute 1 is hidden here and only attribute 2 is shown. And in this transaction, only attribute 1 is shown. So that is possible. So you can have distinct transaction certificates, each exposing different attributes that a user has, right? And you can present that and you can use that to sign transactions. So these transactions will look completely different to an end user. So this way, the eCert is also hidden. So you get complete anonymity and you also get unlinkability across transactions. So the next thing that you can perform with these anonymous and unlinkable transactions, I just hinted at it before, is auditability. So what is possible to do is once I have signed these transactions, I can actually prove to an auditor. So let's say auditor has a particular secret key. I can basically expose this information only to an auditor, and the auditor will be able to verify this transaction to say that this attribute indeed belongs to this user and this is a valid certificate. The auditor will be able to determine that. And not only that, it's not that one auditor will see all the data. It's possible to have per data element auditor or per attribute auditor. So I can say only for this attribute, this person is the auditor. For some other attribute, it can be a different auditor altogether. So that's also a very unique capability that we have in Hyperledger Fabric. And it really gives you a very fine-grained control on exactly what data elements you want to share with whom, including with auditors. So you can say, okay, this data element I will only share with this auditor and not with someone else. Right? So that's also possible. And when I say auditor, it need not be just one entity that holds that key. It's possible to share that key with multiple, or distribute that key with multiple parties. So only if all of those parties come together will they be able to audit this thing. So those are known capabilities in cryptography. Right? So that's the unique notion of auditability that Hyperledger Fabric can give you. And of course, there's certificate revocation. So this happens. This is an important functionality provided by the certificate authority. So it's going to maintain a certificate revocation list of the set of user certificates that have been revoked. So with Identity Mixer, so there is a separate revocation authority, and what is possible is that so basically whenever someone is verifying a transaction, they're going to go back to the revocation list and check whether the certificate is still valid or whether it's been revoked. Right? So to do that, it's also possible to do that in a privacy preserving manner. So all non-revoked users, there will be no loss of privacy because of having this non-revocation proof. To show that this certificate has not been revoked can also be done in a privacy preserving manner. So right now, the implementation for the integration of Identity Mixer with Hyperledger Fabric is going on. It should be out in probably a month or so, I think. It's already in the roadmap for Fabric 1.2 version. Right? So there are libraries written partly in Go, partly in Java, and this is really a new blockchain crypto service provider interface that's being written. So there is a client SDK. There's going to be a new Fabric CA, and of course the membership service provider implementation that provides these functionalities. Okay, so now I'm getting to another very interesting cryptographic notion, which is zero knowledge proofs. So zero knowledge proofs are really almost, they seem like magic, right? So what they are is that I want to be able to prove that I hold a particular secret or that I have some particular private information, and without revealing that information to you, I want to prove to you that I actually have that private information. For instance, one of the things I want to do, one of the common cited examples is I have a driver's license. The driver's license has my age on it. Typically, when I go somewhere and present my driver's license, you will see all the information on it, right? You will see my date of birth, my address, everything, right? But let's say I want to only prove to you that I am greater than 18 years of age, right? I don't want to reveal to you all the other details of my driver's license. Can I do that? So there are ways with cryptography where without revealing my driver's license or my date of birth, I can prove to you that I'm greater than 18 years of age, right? That's pretty cool, isn't it? So that's really the zero knowledge. So you will, once you have the proof, you can be guaranteed that I am actually 18 years of age or older, but I've not revealed I've given you zero knowledge about my private information. I've not revealed my date of birth at all, and there's no way for you to guess that. Right? Another very important use case is my funds, right? For instance, I don't want to reveal my bank balance, but I want to prove to you that I have enough money in my bank account in order to make a payment. Let's say I'm going to pay you $100. All I need to prove to you is that my bank balance is more than 100. I don't have to reveal my bank balance to you for that. Right? So that's again a very powerful notion. There's also proofs about membership, right? So I want to prove to you that I'm a legitimate user of the network. I'm a permissioned user, but I don't want to reveal my identity. So that's also another place where there is zero knowledge is used, where I don't reveal my identity, but I prove to you that I'm authorized for access. Right? And of course, asset ownership. I want to prove to you that I own an asset without revealing to you what that asset is. Right? So there are multiple of these use cases for zero knowledge proofs, and this is actually in cryptography. This started way back in the 1980s. Over a period of 30 years, it's actually matured to a good extent. And now with blockchain coming into play and privacy being an important aspect of applications being built on top of blockchain, people are asking for these privacy notions. Zero knowledge proofs have seen a resurgence over the last maybe 3-4 years. There's a lot of work going on in zero knowledge proofs. And let me give you a few examples, right? Identity Mixer with the transaction certificates actually uses zero knowledge proofs, where the user can prove to you that this T-cert was in fact generated from a particular E-cert without revealing that E-cert to you, right? So that's in the identity space. Likewise, Hyperledger Indy, which also focuses on identity, can prove to you certain claims about your identity. So claims are issued by different people, and I can prove to you that I have a particular claim without revealing that claim to you, right? And it's also possible to integrate it with transaction validation. So this is with the state verification, whether the inputs and outputs of a transaction, it's possible to validate that. So I'll come to that in the next slide. And an important property of these zero knowledge proofs is that the proof is actually time consuming to create. And even with the private information, it's going to be very hard. It's computationally intensive for the owner of the information to construct the proof, but verifying the proof is very simple. So you can the verification can be done by a large set of independent parties. They can all verify it very quickly, but construction of the proof is very, very difficult. So that's the cryptographic property that they have. And of course, if I do not have the private information, it is impossible for me to match a proof and to make you believe that I actually have that information. So without the private information, I can't fool you. So you can be guaranteed that it's impossible for me to generate the proof without the private data. Okay, so let's look at a few other examples where zero knowledge proofs are employed in a very nice way, right? So ZeroCash is a very nice example. So what they have is a zero knowledge proof for providing full anonymity of users, right? So remember that Bitcoin and Ethereum only provide pseudo-anonymity, right? They don't give you full anonymity, right? So what they can do with zero knowledge proofs is that they can prove that they can ensure that the user identity is never revealed when someone looks at a transaction, right? They can also conceal the asset value. So in Bitcoin, for instance, everyone who is looking at the network can see, by just looking at a particular transaction, they know exactly how many Bitcoins got transferred from one Bitcoin address to another. So that Bitcoin value is not private. But what ZeroCash allows you to do is to conceal that value, right? And so the way we'll talk about how it does that in the next slide. And the other thing it can also do is conceal the UTXO graph. So basically the list of unspent transactions, that can also be kept private. So ZeroCoin was introduced as a cryptocurrency as an extension to Bitcoin. So they actually forked from Bitcoin and they created a new cryptocurrency based on ZeroCash. It was called ZeroCoin. And in 2013, they actually showed a 98% smaller proof sizes. So they dramatically improved the complexity of these proofs. The size of the proof became very succinct. And the time taken, but the time taken is still a concern, right? So this still takes a significant amount of time and computational effort to construct these proofs. So that is still a concern, and it's an active area of research. And this whole ZeroCoin notion has been integrated now with Ethereum and Quorum. So it's possible in Ethereum to conceal the transaction information, right? So who's transferring how many ethers to someone else. And the ability to verify these zero knowledge ZK snarks, as they are called, on chain is now inbuilt into Ethereum and Quorum. So we'll look at Ethereum and Quorum later in this lecture, but this has been incorporated there. So let's quickly look at how this works, right? So in any Bitcoin transaction or a Ethereum transaction, basically any UTXO, there are a certain set of inputs and a certain set of outputs. And what we are doing when we change these transactions together is that every transaction needs to prove that the inputs are all unspent. So they have to be unspent outputs of other transactions. So there are these links in some sense. And what we want to hide are the following, right? We want to hide the amount of value that is getting transferred, the in and out, right? How much is the value of the transaction? We want to hide the identity. So I talked about hiding the identity. And we also want to hide the UTXO pool. Now, if you look at the validation logic or the prevention of double spending, what we want to ensure is just that the outputs are not more than the inputs. In some sense, we are not generating new assets or new money out of this, right? The outputs have to match the inputs. All we have to prove is that property, right? We don't have to reveal exactly what the inputs are, what the outputs are. So those values can be hidden, but I prove to you that outputs are not more than the inputs. So that proof is sufficient for you to ensure that there is no double spending, right? So that is provided through a zero knowledge proof. So someone who is submitting this transaction has all of these inputs and outputs obfuscated. Along with it, they submit a proof saying outputs are not more than inputs, right? Anyone in the network, all the peers, let's say Bitcoin or Ethereum peers, they can all verify that outputs are not more than inputs. So it's a valid transaction and they can admit it. And what is also great is that the set of unspent transactions can also be kept private. So no one at any point of time, even the peers, will not know what the set of unspent transactions are. But what they can verify is membership, right? I can verify that this particular input is an unspent transaction at this point. It is part of this private set in some sense. That set is kept private. Even the peers don't know it, but I can prove that I belong to that set. So isn't that cool? That's really a very cool property. There's very involved mathematics in this, all of which I myself do not understand, but the properties are very, very useful in many enterprise applications, right? And these are becoming reality today. So we are actually starting to use these very complex cryptographic primitives for providing privacy in blockchain platforms. Okay, with that, we've come to the end of this lecture. We will look at a few more, at least one more privacy primitive in Hyperledger Fabric in the next lecture. But in the meanwhile, there are a few interesting reading, right? So there's a lot of interesting work going on in this space, as I said. This is a great topic for research if you're looking for like a thesis topic. So let's go over what some of these things, right? So there's a nice TED talk, a TEDx talk on using the Bitcoin blockchain to detect fraud. So this is really from by a lawyer in the US, where they actually monitored transactions on the Bitcoin blockchain to detect people who are doing some fraudulent transactions. So I won't go into the details, but it really tells you two things, right? One is how Bitcoin actually doesn't give you the privacy, but at the same time, because of the fact that blockchain immutably records all transactions that have happened, it's actually possible to go back in the past and know exactly what happened, who did what. So the provenance is great for detecting fraud, but at the same time, there is privacy concerns in the Bitcoin blockchain. So that's a very interesting, it's about 20 minutes, I think. It's a very interesting TED talk. Identity mixer, so you can find out more details. If you are into security, into cryptography, I would encourage you to take a look. So this is completely open source. Identity mixer itself is open source. There's a lot of material for you to look into the details. There's a nice overview set of overview article, and there's a link to the GitHub itself, including documentation. And if you're interested in zero knowledge proofs in particular, the Wikipedia is a great place to start. It gives you a nice overview of concepts. And the ZeroCash project itself is a very interesting project. So I would encourage you to read that. They have a research paper in the IEEE Symposium on Security and Privacy, which is also a very good read. So I'd encourage you to dig deeper into this topic if that interests you. And with that, we'll get to the next lecture. We'll look at one more construct for privacy. Thank you.